Hi, my name is Dr. Ahmath. In this video lecture, we are going to discuss about the equations of lines using vectors. Well, conventionally, we are going to define the equation of the lines as y is equal to the kx plus b, where k and b are going to be the two attributes, parameters of the line, and by just playing with them, we can find the coordinates of the points along the line. So actually, the reason why we would need the equations of the lines is to be able to find the coordinates of the points along the line. So let's say you are given some point here with the coordinates x and y, and you can find the x coordinate of this point if you're given the y, and you can find the y coordinate of this point if you're given the x. Well, for example, if you are given the equation of the line y is equal to the 3x plus 1, and if you are given that x should be equal to the 3, then you can just substitute this to the equation of the line and find that the y coordinate of this point along this line is going to be equal to the 10. The problem is arising when we are go to the higher dimensionality. So if we go to the 3D now, where the points are going to be given, defined with the three tuples, so here x, y, and z, we can't really define the lines using this equation anymore because it doesn't give us the z coordinate of the points. So we need to figure out a general tool, some general tool which would able to us to define the lines, which would able to give us the coordinates of the points on the line using the vectors, for example. Well, in any dimensionalities, not only in the 3D, but maybe in the 4 dimensionalities, 5D, and so on. And one of the ways how we can do this is the following. So I'm going to go back to the 2D in order to express all of the ideas easily. So let's say now, instead of just defining the point, I would like to define the vector, which is going to point out to this point. Well, if you remember, the position vectors are always start from the origin and end at some point. So I would like to define the points along this line, not just the point, but as the vectors. So this vector r0 is going to be, is going to have the ending point on the line. So I would like to be able to define any point along this line, for example, this point, for example, using this kind of vectors. Well, if you remember, we discussed about the geometric operations with the vectors. And we've seen that you can just multiply this vector to some constant in order to scale this vector, right? So you can, if you multiply this r0 to 2, it is going to be the vector which is twice longer than this vector, but we can't really just change the direction of this vector. Well, if you would like to change the direction of this vector, you need another vector. So it appears in order to define the points along this line, we need another vector, not just one vector, but another vector which is going to be parallel to this line. So this v vector now is going to be a vector which is parallel to this line L. So how we can get the points using this v vector and r0 vector? Again, so you are given now the two vectors, r0 vector, which is a vector which points out to any point along this line, and the v vector, which is any vector which is parallel to this line. So if you add these two vectors, you're going to get another vector which points out to a point along this line again. If you remember, the way how we are adding these two vectors is to create a parallelogram. So I'm just going to copy one of these vectors to the end of the first vector. Then the diagonal of this parallelogram is going to be an addition of these two vectors, which is going to point out to a point along this line. So I'm going to denote this r. So the r vector here is obtained as the r0 plus the v, right? So now the question arises, hey, so how I can find any point along this line just using these two vectors? So the key is by just scaling, by just working with this v vector, you can reach any point. So where we can reach out any point by scaling, or by just changing the lengths, by changing the lengths of the vector v. it appears. Well, for example, if you just multiply this v vector to the 2, you're going to have this vector. And if you just add this to the same vector r0 now, you're going to have another point on the line. So let's assume now you would like to find the coordinates of this point using some vector r, right? So how you can do this? Again, you're going to scale this vector v. So you need to scale this vector v by just multiplying this as a -1, right? And if you add this to the r0, so this is r0 again, so the r0 plus minus v is going to give you this black vector again. So I'm just going to write down the black vector here. This black vector was equal to the r0 minus the v. So this is the r is equal to the r0 minus the v. So if you remember, this point or this vector was simply r is equal to the r0. And if you remember, there used to be another vector here as well, right? Another point. So here, let me write this as well. So this r was equal to r0 plus 2v. Right? So now let's look to the structures of all of these vectors. The structure was like this. So the r is equal to the r0, or r is equal to the r0 plus the v, or r is equal to the r0 plus the 2v, or r is equal to the r0 minus the v. Well, can you guess what is going to be the structure of the vector equation of a line? Well, yes, so the vector equation of the line is going to be the vector r, which is going to give you a vector which points out to any point along the line. So now this vector can be any-dimensional, right? Is equal to r0, so we need one vector, so which points out to one of the points, to any point on this line, plus the v, which is the vector which is parallel to this line, times to the t, which is going to be now our parameter. So by just changing the values of the parameter, we can reach out different points along the line. So this is the point of creating the equations. The equations, we need equations in order to reach the different points along the lines. So here the t is going to be the parameter, and if you see here that the t is equal to the 0 is going to give you the first point. When t is equal to the 1, you can reach another point. When t is equal to the 2, you can reach again another point. When t is equal to the -1, you can reach this point, the last point. So by just changing the parameters, by just changing the values of this parameter t, you can reach actually any point along this line. Well, this equation is called as a vector equation of a line. So let's do an example. So find a vector equation for a line that passes through the point and is parallel to the vector v. And actually, the line which is passing through this point A means that we can describe this point A as the vector r0, whose ending point is going to be equal to the 5, 1, and 3. Right? And also we're given a vector v which is parallel to this line, which is given as a 1, 4, and -2. And the vector equation of this line in 3D is going to be simply r is equal to the r0 plus vt. And now I'm just going to plug in r0 and v into this equation in order to derive the vector equation. It is equal to the 5, 1, 3 plus 1, 4, -2 times to the t. Well, I can multiply the t to this vector, to this vector here. So by just multiplying every component of this vector to the t. So then I can write as 5, 1, 3 plus t, 4t minus 2t. And now I can add these two vectors. So since I've got the two vectors from the same dimensionality, which are given with the 3 tuples, right, which have the 3 components essentially, I can add these two vectors component-wise. It is going to be equal to the 5 plus t, 1 plus 4t, 3 minus 2t. So this is going to be the vector equation of this line. Well, it is important for me to understand what I've got. So I've got r vector which points out to any point along this line. So if I just change the values of the t, it's going to give me always the points along this line, right? So if the t is equal to the 0, I will get r0. If the t is equal to the 1, I will get another point, and so on. So the r is going to have, again, the 3 components, which is going to give me the coordinates of the point, like essentially x, y, and z coordinates of the point. So you can see here that from one side, r is the coordinates of the point. From another side, this is this equation. It means that the x coordinate of the point along the line is going to be equal to the 5 plus t. Y coordinate of the point along the line is going to be equal to the 1 plus 4t, and the z coordinate of the point along the line is going to be equal to the 3 minus 2t, which is nothing else as the parametric equation of the line, right? So if you remember, the parametric equations are given, are going to describe the x, y, and z coordinates of some curve using some functions which depends on the parameter t. Right? So this is exactly the parametric equation. So essentially it appears the vector equation is nothing else as the parametric equation of the line, where the t is going to be the parameter which takes any real value. Well, let's do another example, which is going to be a little bit difficult, or different, I would say. So find the parametric equation now of a line which passes through these 2 points, A and B. So previously, you were given just one point and the vector which is parallel to this line. Now you're given 2 points. So again, in order to derive the equation of the line, the vector equation of the line, I'm just going to use this equation. R is equal to the R0 plus VT. So, well, you are given 2 R0s actually. You can find this R0, you can take this one as the R0, or this one as the R0. It doesn't matter, right? But the problem is you are not given the v vector. So if you remember, the v vector is the vector which is parallel to this line, and it is not so easy, it is not so difficult to get this from these 2 points. So what I'm going to do is I'm going to create this vector which connects A and B. So if you remember, the AB vector can be obtained by subtracting the coordinates of the starting point A from the coordinates of the ending point B. So it is going to be equal to the 3 minus 1 and 1, minus 2, 4, and minus 3. And if I subtract this, it is going to be equal to 1 minus 1 minus 4, it's minus 5. 1 minus 3 is going to be 4. Well, that's going to be the vector which is parallel to this line, which is nothing else as the v vector. Then I just need to substitute everything into this equation in order to derive the parametric or the vector equation of the line. It is going to be r is equal to, so r0, which can be any of these 2 points. So I'm going to take the a as r0, 2, 4, and minus 3. Plus the v, which is 1 minus 5 and 4, multiplied to the t. So the parametric equation should give you the x, y, and z as some functions of the t, right? So that is why. So I multiply this t to this vector and add this to this one and find out every component of this vector. So the x component is going to be equal to the 2 plus 1 times the t. Y component of this vector is going to be equal to the 4 minus 5 times the t. And the z component is going to be equal to the minus 3 plus 4 times the t. Well, that's going to be the parametric equation of the line. So in this video lecture, we've learned about how to find the equation of the lines in any dimensional cases using the vectors. And also we figure out that vector equations of the lines are nothing else as the parametric equations. So essentially you can reach out any point along the line using the parameter, one parameter t. Well, thank you very much for your attention. I hope that this was helpful for you.